Yeah, so it's a great pleasure to welcome Kathleen Jones, who's giving the next keynote presentation. So I found a brief biography online. So Kathleen studied physics at Texas A&M University, and then did a PhD in physics at Caltech. And she's currently a radar scientist at NASA JPL. And Caltech, focused on using radar for natural disasters and monitoring critical infrastructure. Been using a number of techniques, including UAV SAR. She also was David Beckart's boss for a while, I believe, who we all know well in COMET too. And I particularly asked Kathleen onto this to give a keynote today because she is the applications lead for the NISAR science team. I know that's a mission that's very interesting for many of the things we do in COMET. So over to you, Kathleen.
Thank you. Are you seeing my screen?
Yes.
Okay.
Thank you.
Well, thank you very much for inviting me. This was quite the surprise and a pleasure to be able to talk at your meeting. As Tim said, I am the applications lead for the NISAR science team, and I've spent my entire career at JPL working on UAV SAR. And specifically for hazards and critical infrastructure monitoring. So I'm going to talk a little bit about UAV SAR and what I've done with that, and then talk about NISAR. And those should be split about 50-50. And the first one will be heavily bent on results, and because I've used UAV SAR, and the other will be heavily bent on the technology because NISAR hasn't launched. So let's see if I can go. So NASA has a SAR program right now. The L-band SARs are UAV SAR, which is a NASA Airborne Science Program instrument. And in the future, we intend to increase the number of frequencies and turn it into a multi-frequency system. Perhaps adding S-band like NISAR will have. And of course, it's already got variants of P and Ka band. And then NISAR is coming online. It's being built now, and I'll show you at least one photo of the hardware just to give you a sense of the scale. UAV SAR is, as I said, L-band. It's got a bandwidth of 80 megahertz, which gives it an intrinsic resolution of 1.8 meters in the slant range, and it's about a 1.5 meter long antenna, so it has a 0.8 meter intrinsic resolution in the azimuth. It's a full quad pole instrument. Almost every data set that is acquired, regardless of what it is being used for, is acquired in quad polarization mode. And so even though the instrument was actually paid for mainly from the Solid Earth program at NASA, it has been used extensively for polarimetry because of the quad pole data that's available. It's got the normal things that are great for airborne science, very low noise equivalent sigma naught, allowing you to do a very high, very detailed studies in radar dark environments. So things like oil spills or something that really the science for studying oil spills has been changed by this instrument. So to get on with it, I just want to give you a brief overview of how UAV SAR has been used for science and applications. And so I put this pie chart here, and just to show the range of science topics and applications that have been used, the UAV SAR has been used for. And on the right-hand side, I just took a selection of different publications among really literally hundreds of publications that have used this instrument. The critical infrastructure studies and hazard studies that I personally have been involved here are listed here. And the two that I'm going to talk about today are the Sacramento-San Joaquin Delta levee studies and the California aqueduct studies. And I just want to take a brief digression and explain to you why California is the perfect place to study water infrastructure. So you probably think of California, maybe you think of beaches or Hollywood or movies and very beautiful environment, but I'm here to disabuse you of that notion. So California is all about water. It is a land of water conflict. This photograph here is of the Los Angeles Aqueduct, which was built in the 1910s, and it actually sparked what is known historically as the water wars between Los Angeles City and the farmers in the Owens Valley, because Los Angeles obviously was growing and it needed water, and so it took it from Owens Valley. So that apocryphal saying attributed to Mark Twain over there, whiskey is for drinking and water is for fighting, just defines California. It is true. It was true in the late 1800s. It was true in the gold rush years, and it is definitely true today. So what makes California water issues so controversial is that there's a great mismatch between where rain and snow falls in California and where people live and people use water. So you've got a lot of precipitation in the north, you get very little precipitation in the south, and people live in the south, and people live in the central part, and agriculture in the southern 2/3 of the state uses approximately 70% of the water usage in the state. So that means that water has to be conveyed across the state. But to make things worse, California has the greatest variability in precipitation of any of the states in the United States. So if you look at the history of positive, floods in California, that's the blue lines over there, versus droughts in California, the red, water deficits, you see that there's been a lot of droughts and a lot of floods. Just for example, here I show the situation in 2016, which was at the end of one of the most significant drought periods in California's history, when say half of the state was in an exceptional drought situation, and that half of the state was in large part where precipitation and snowfall occurred in the Sierras. On the other hand, in 2017, it was a very wet water year. The reservoirs filled back up. The highest dam in the United States, the Oroville Dam, had a near overtopping event, and then the abutment was degraded and eroded, and there was a huge flood through that area. So that's in 1 year that difference occurred. So California is all about water capture and conveyance. If you look at the figure on the right, all of the blue lines are the major rivers, and if you try to block out the other color lines, what you notice is that most of the blue lines form a funnel, and they funnel into San Francisco Bay, and they funnel through the Sacramento Delta. And so the Sacramento Delta is the major water source for the state of California, and California has a Department of Water Resources, and they are intent upon maintaining that water supply. On the other hand, the Sacramento Delta has been used extensively for agriculture, and it was an inland wetland, and it was levied in order to form islands that could be used for agriculture. This was starting in the late 1800s and extending through about 1930 or so. The land was divided up into islands. If you look at the photograph over there on the lower left, then you look carefully, you can see that those levees are, that the land behind the levees is much lower than the water level in the channels. And so about 1,700 kilometers of levees protect that delta from inundation. Most of the delta is below mean sea level. Then there's the California Aqueduct, and that's this red line here, which supplies water from the delta down to the cities in the south, the huge cities, Los Angeles, and then to another aqueduct down to San Diego. So a fair fraction of the water in those cities come from the Sacramento Delta. And that aqueduct and another aqueduct that also feeds from the Sacramento Delta supply water for the agriculture in the Central Valley, which is, let's see if my in here, this is a Central Valley of California extends through here. So what we did with UAVSAR was shortly after the plane air instrument became operational, we were funded to do a study of the levees, levee stability in the Sacramento Delta and subsidence in the Sacramento Delta. So we collected 9 tracks, about 55 acquisitions between 2009 and 2016, and formed them into about 1,500 interferograms across those 9 different tracks. This was the work that David Beckert did with me whenever he came to JPL. And if you look at this, stack of wrapped interferograms shown here, you can see that this is the area that is the delta has very low coherence. And so a lot of work was done to get reasonably good subsidence measurements from this data. And probably the hardest part was doing phase unwrapping in that area. You had a bunch of islands and low coherence. And so we had developed a method where we took the interferograms, which were already multi-looked to 3 by 12 to form about 7-meter resolution pixels. And we multi-looked them further to form low resolution wrapped interferograms. We unwrapped them with snafu and using a low coherence pre and post processing, where we basically replaced very low coherence pixels with the nearest neighbor high coherence pixels to try to aid in the phase unwrapping. And then we did a closed loop iteration where we looked at phase closure in order to do corrections, and then to use that low resolution unwrapped interferogram as a mask for unwrapping the 9 pixels that were within high resolution pixels that were within each of these low resolution pixels. And so that gave us a stack of unwrapped interferograms, and we used giant SBAS in order to do small baseline subset in SAR processing, time series processing. So that gave us a line of sight map for each line. And in this line that's shown here, if you look at the left, you can see kind of a straight line running down that particular swath, and that is the Hayward Fault. So to the left of that is South Bay Cities, Fremont, and San Jose. So that gave us these maps of the rate and the rate uncertainty. And for example, I show here the subsidence heterogeneity. So we plotted 2 points within one island of the Sacramento Delta. So these are separated by a few kilometers. And you can see that in one case, you have very clear seasonal signals. That's the one on the left. And very high amplitude seasonal fluctuations in the surface level, and a very reasonably large trend in subsidence of about 12 centimeters over the 6-year period. And then a few kilometers away, you have very low subsidence area in the same island. And that's because of the heterogeneity of the soil and the thickness of the peat layers, and the presence of old meanders through these islands, which give very sandy soil with very low compaction rates. So we looked at levees. Of course, we were intent on looking, in addition to subsidence overall, looking at levee threats. And the kinds of things we were looking for were cracks, seepage, slope instabilities, and just general subsidence. So that picture on the lower right-hand side, here you see in the background, you see a dip in the road. When that road was built, it was graded. So you see very clear heterogeneous subsidence along this road. And all of the roads on top of the levees in the delta are like this. You'll be driving along, and it's like a washboard, undulating surface. So we used INSAR to look for these kinds of land movement, and we used some pulsar data and coherent change detection to look for seepage. So I'm going to show you an example from levee deformation only, not the seepage in this case. So this location here is an earthen levee. This is a typical levee in the Sacramento Delta. They're almost all earthen sides. I personally can't think of anything where the land side slope is not an earthen levee slope. These are not your pampered levees of the Netherlands. These are roughly maintained, well maintained for U.S. levees, though, given that California is a relatively rich state. So what I'm showing here is the worst levee in the Sacramento Delta. And it's kind of hard to see, but there's a crack that runs for several hundred feet along the edge of this levee. And it's pretty invisible. And given that the way that people monitor these levees is by driving along and looking for problems from the road, or walking a particularly suspect area, this is very difficult to monitor these 1,700 kilometers any other way than with remote sensing. So this is the subsidence map from that site that I just showed you where the levee crack occurred. And you can see that in that particular area, you've got something like 12 centimeters per year of subsidence of that long stretch of levees. This was published by David and the other members of the team a few years ago. So we also, while we were flying up and down to the Sacramento Delta, which is up here, we were actually flying right over the California aqueduct. And so the state came to us and asked us to image the aqueduct whenever the drought started, whenever it was obvious in 2014 that there was a major drought. And we had actually started acquiring, turning on the radar for one section of this in 2013, just to try to get some data over the California aqueduct. So the Central Valley is a semi-arid region. The agriculture there initially, whenever people first started farming that area, it relied upon groundwater. And if you look over here at the photograph on the right-hand side, you can see 52 years of subsidence, what 52 years of subsidence in that particular area looked like. It was an awful lot of ground level change, and it came from groundwater withdrawal. Well, this became an issue, and they built aqueducts in order to supply surface water so that the agriculture could stop relying so heavily on groundwater. But when there's a drought, surface water deliveries are curtailed or halted, and during that time, the farmers use groundwater, and so during the 2013 through 2016 period, they did do groundwater withdrawals increased substantially in that area. And this can lead to aquifer compaction and loss of storativity whenever new lows are reached in the water table. So we started looking at this in 2014, and very quickly it became obvious that there was a substantial hotspot of subsidence that just the aqueduct went right through that particular subsidence bowl. And the photograph that I took on the right shows you what that area looks like. There is no way that you could identify that this was a subsiding area other than using something like INSAR. So we went to the state and we showed them this particular image as soon as the interferogram, as soon as it became obvious that there was a problem. It was something like 8 inches of, English units, of subsidence occurred between May of 2014 and October of 2014. That's an awful lot of subsidence in 4 months. And they had no idea that such rapid subsidence or such localized subsidence could occur. They were most concerned about this area up here, which was historically subsiding and which the aqueduct passed right through. But they went out and did leveling surveys and they validated that. So we continued to monitor the progression of that subsidence bowl, and it seems what we were seeing back in August and through October of 2014 was a minor contribution to the amount of subsidence that eventually occurred. Ultimately, we were seeing something like 60 to 70 centimeters of displacement in that area and 11.2 kilometers of the aqueduct that had subsided more than 10 centimeters. During the wet year in 2017, much of the other areas in the Central Valley had experienced rebound, refilling of the aquifer, but this particular area had a minor recovery, and then the next year was a normal to sort of dry water year, and subsidence reinitiated, continued in that area. So that's what I have for the critical infrastructure work that I'm showing, and so I'm going to move on to talking about NISAR. So NISAR is a collaboration between NASA and the Indian Space Research Organization, ISRO. The launch date, launch is set to occur from India in May of 2022. I can say that that date will almost certainly slip because of the delays from COVID-19, but we are trying very hard to not slip back past September of 2022, because then there's an eclipse period, and during that time we can't launch because of the amount of power that we would have on the solar arrays given the orbit that we'd be in. And so if it's delays past September or October of 2022, then we would launch in January of 2023. So ISRO is supplying an S-band SAR for that, and NASA is doing the L-band SAR, and UAV SAR is kind of the prototype, airborne prototype for the NISAR L-band SAR. So our science objectives are threefold. We focus on solid earth science, on cryosphere, and on ecosystems. For solid earth, the focus is on earthquakes, volcanoes, and landslides. For cryospheres, we're looking at ice sheets and glaciers and sea ice. And for ecosystems, we're looking at wetlands, agriculture, and forests. So it's a very broadly capable mission. In addition, there's a component for applications, and there's a requirement that NISAR respond provide urgent response data during disasters. And there's a very strong interest in using the data that is acquired for science in hazard mitigation and for other applications, for example, agriculture monitoring, giving this information to the agencies who are responsible for looking at food security, not just in the US, but also worldwide. Some characteristics of the instrument. It's L-band. There's an S-band instrument. It uses a new sweep SAR technique to get an image swath of 240 kilometers, and that is regardless of the polarization mode. It has single, dual, and quad pole capabilities, with most of the data to be acquired in dual pole mode. It's got a 12-day repeat for INSAR, and of course, it's got different modes for bandwidth. So in the 80 megahertz mode, you get a 3-meter ground resolution, and 40 megahertz, 6 meters, and then about 12 meters in 20 megahertz mode. And I'll talk a little bit more about which modes are going to be used where later. It has a left-right pointing capability, and now the mission is going to be left-looking, which is in contrast to many of the other missions, satellite SAR missions, which are right-looking. And I'll talk about how what that gains us later and what that loses us later. So it has, you get about 2 to 5 passes over any site, depending upon the latitude. Of course, at the equator, you get 1 pass, and data is acquired in both ascending and descending mode. You have about 33 degrees to 47 degrees pointing angle range across that 240 kilometer swath. We use a 12-meter diameter reflector, and the one photograph I'm going to show you is of the 12-meter reflector deployed, the one that will be launched. The sweep SAR technique works as follows. On transmit, you illuminate the entire swath. That's and then on receive, you steer the beam to acquire the data across 4 different incidence angle ranges. And then on board, you do processing to filter and combine those beams into one synthesized beam for return. That is kind of illustrated over here on the right. And this allows an echo to span more than 1 inter-pulse period. And it is a huge advantage to be able to get a 240 kilometer swath, regardless of the ground resolution. So the modes, we use for most of the global coverage, we use a 200 megahertz plus a 5 megahertz beams. So you have a band that's 200 megahertz wide, and then separated from it is a 5 megahertz band, and that is used so that you can do ionospheric corrections from a split beam technique. There is an augmentation which allows the 40 megahertz mode to be used over North America. That was an augmentation that was funded through the US Satellite Needs Working Group, and it provided an additional ground station so that we could acquire higher resolution data over North America and Hawaii. So this lower band, HHHV, and the upper band, HHHV, is a default mode for the globe coverage. And there is another option where you change the polarization between the lower band and the upper band. This would allow you to do better measurements of soil moisture. But what we're going to do is do the HHHV here and then a 5 megahertz VVH mode here. This shows the coverage, global coverage, near global coverage in the left-looking mode, and each of those different colors is a different mode. And if you're interested, I have a chart that I can show in the backup slides that show what each of these modes are. Across North America, you have that 40 megahertz mode. You have a high 80 megahertz mode over parts of the ice sheets, single polarization, dual polarization, dual frequency modes over Indian areas of interest, which include Indonesia. And then we have the higher resolution mode over some urban targets. The specific urban targets that are selected have been down sampled from the set that's shown here in order to fit within the data volume, the downlink data volume. Downlink capability is a limitation on the data volume that can be acquired with NISAR. So NISAR was originally going to be a right and left looking mission. It would spend 9 months in right looking mode and 3 months in left looking mode. However, that was, shall we say, suboptimal for INSAR and solid earth and critical infrastructure monitoring. We're having a 3-month gap in your time series would cause problems. So there was a decision made to go to a left-looking mission only. And left-looking allows you to do more imaging of the Antarctic. So you have a larger hole in the Arctic, which gives you poorer coverage for sea ice, and you have a much reduced hole for Antarctic, which gives you better coverage of the ice sheets on the Antarctic continent. The decision was made that since other missions, in particular Sentinel, is right-looking, there will be data available to mitigate the Arctic coverage loss from NISAR. This is an instrument layout. It's your standard satellite SAR, solar arrays, a very large antenna, reflector, and the S and the L band feeds are shown here on top. So this is the photograph of that 12-meter diameter reflector array, and here you show it as it's being tested and deployed for the first time. Very nice. So I spoke about the Satellite Needs Working Group in the U.S. All of the federal agencies have contributed members to a Satellite Needs Working Group, and that reports to NASA and to the federal government in general, the White House, the remote sensing observation needs of the different agencies. And as a result of the 2016 Satellite Needs Working Group recommendations, the NISAR project was directed to augment the downlink system so that you could get higher bandwidth data over North America. That allowed an increase in the downlink capability from 26 terabits per day to 35 terabits per day. This shows the data analysis stream. All of the data will be freely available from the NASA's data archive centers. There will be SLCs available at level 1, some interferograms, and then level 2 will be the geocoded products polarimetric images and interferograms and unwrapped interferograms. Level 4 data is shown, products are shown here. They will be provided only for validation data sites, which are extremely limited around the world. And but if you look at what the Satellite Needs Working Group augmentation has allowed is a global soil moisture product, and also global inundation products are proposed, and other ecosystem-specific products, and also a line of sight displacement product similar to what is available from Norway, that Norway has implemented. So I think I'm going to summarize here and just say that UAVSAR has really been widely used, and if you haven't seen the data or used the data, I encourage you to look at it. There's a lot of data that is available using methods that aren't available from satellites, like very rapid time series and very short repeat interval data that allows you to do dynamics of processes that you couldn't do with the kinds of satellites that are available now. For NISAR, we really have tried to address a very broad range of key science questions, and all of the data, like all of NASA's data, will be available free and open. Currently, if you're interested in NISAR, then we've also taken UAVSAR data and made NISAR similar simulated products, and those are also openly available. So I'll leave you with this to look at this slide while I answer questions. Thank you.
Thank you. That was fantastic. Thank you very much for that overview of those two different areas. That was great. So I guess I'd seen the reflector in images, but actually seeing the photograph of it gives the sense of scale, which I hadn't fully appreciated, I think. So it's great to see that. So let me go for questions. I started to come in. So Valerie Kayol has asked, isn't the connection of the reflector and the rest of the satellite a weak point? And if so, is there a plan B to operate the radar without the reflector?
There's not a plan B. The reflector is, it is highly engineered, you're right, it is a problem, a potential problem. SMAP has a 6-meter reflector on the same type of boom structure, and NASA tests these things like you would not believe. Anyway, I sure hope it doesn't fail. I'm more worried right now about the launch than about that.
Great, thank you. So I guess my question was about NISAR 2, really. So I mean, it's taken so long to get to NISAR 1, and the various iterations of different missions over the last 15, 20 years. You'll know better than me about those. So is there a plan for a follow-up mission, and how long will NISAR 1 last, if all goes well?
If all goes well. NASA always has a very, the requirement is that NISAR lasts 3 years in the L-band SAR and 5 years for the S-band SAR. NASA instruments generally, but not always, last longer than that, so we expect it to last more than 5 years. It has all of the necessary propellant and so on to last for much longer than a 5-year mission. There is a recommendation for a NISAR-like follow-on, the Surface Deformation and Change mission, and that is currently in formulation. There are many different potential architectures are being considered, including a straight-up follow-on for NISAR. One issue with that is that NISAR is an expensive mission, and the surface deformation and change mission is supposed to be substantially cheaper. So partnering with an international agency on, if there were to be a follow-on for NISAR, much like we've done with India now, would be critical, I think. Yes, we all want NISAR to be to last much longer. And I want it even more than most. And that's actually why I'm the applications lead, because the more federal agencies that find this data useful, the more essential it is. So,
yeah, I mean, I think that's something we've seen with Sentinel-1 as well, is the just that knowledge that that mission's going to be there for a long time actually sets up a whole bunch of things that you wouldn't or couldn't do otherwise, and the open data sharing as well. So it's exciting that NASA will be doing this. So another question from Pablo Gonzalez: are there going to be simultaneous acquisitions from the S and L band sensors?
Right now, those simultaneous acquisitions are over selected CalVal sites and over the Indian areas of interest. There's a lot of conflict on the science team to get everyone's science done. But one of the recommendations is that more L and S band simultaneous acquisitions be acquired over different sites globally. So that's not currently in the plan, but we have a few years to launch to do that kind of replanning, and it is an exercise that we will do.
Great, thank you. And also on the theme of different wavelengths, as Simon Dahl has asked, did you compare L-band and C-band INSAR products over wetlands, for example, decorrelation after rain or changes in penetration, noise characteristics, coherence, etc.?
I did a little bit of that for the Sacramento Delta. I got some X-band data and some C-band data, and the L-band coherence is much higher.
Yeah, great. And Yasser Maksudi asks, is the quad pole data acquisition available for both L and S bands?
For NISAR, no. There's very little quad pole data that's going to be acquired simply because of the data volume, and the noise equivalence, the noise spectrum is sufficiently higher for quad pole data that the swath width has to be narrower in order to meet the requirements on noise figure. So there isn't going to be a lot of quad pole data acquired.
Great. John Elliott asks what the duty cycle is. So can you collect data on every pass for the whole globe?
Yes, we collect the data on every pass.
Fantastic. Yeah. Great. And yeah, I guess the follow-up question to that is about the data distribution infrastructure, which ESA basically put Sentinel-1 up there before they had the infrastructure for disseminating the data ready. So what work are you doing on the data dissemination infrastructure?
Yeah, we're working with the Alaska Satellite Facility for distribution of the data, and we've done things like tested the speed of transfer to see that we can, with 35 terabits per day of data coming down, you better process that data in one day, or you very, very rapidly fall behind to the tune of years. So the idea is that data will be processed within 24 to 48 hours and delivered to the DAC during that time. And so that kind of speed of processing has been tested, and also the transfer has been tested. So we're working very, very closely with ASF so that the data is available after being acquired.
Great. I think that's the last question that's been posted. So let's all, if you want to show your videos and maybe unmute your mics and give Kathleen some appreciation. It's very hard to do these kind of presentations to blank faces, but there have been around more than 80 people watching live, and we'll also record it and we can discuss afterwards whether you'd be happy having it online or not. We can chat about that offline. So thank you very much.
Well, thank you. That's great.
Great. So next up, so you're welcome to stay. We're going to have a social kind of quiz type activity that Charlie is running. You're also I know, very busy, so you're welcome to say goodbye as well. We'll leave that up to you.
Yeah, I think I'm due on my next telecon in 15 minutes. So.
Okay. Yes, good. Okay, thank you again for joining us. That's great.
Thank you.
Oh, hi, Elias. I just saw you there. Nice to see you. And Charlie, are you going to tell us? Do we want to give people 5-minute comfort break?
Yeah, I think so.
And I'm here to grab a a cup of tea or a beer or whatever people want.